Hello and welcome. So, we are studying function generators and oscillator circuits. So far we have seen two such circuits, 555 timer and another one which is made up of a Smith trigger and a integrator. So, recall this. So, in one of our circuits we had a Smith trigger and an integrator, and we connected them in a loop. The output of the Smith trigger goes to the integrator. Therefore, the output of the integrator changes continuously, it increases or decreases, and at some point it triggers the Smith trigger to change its output, and this way this entire system oscillates between two stages, two states. Another circuit, let us see, which is a simplified version of this, where we can replace this integrator with just a RC circuit, capacitor resistance circuit like this. So, okay, just see that this actually is also a kind of integrator circuit, kind of integrator. Why? Because if you say if you ground this and if you apply a voltage here, say this is V VA, if this voltage is VA, then this voltage, call this VC, which is the voltage across the capacitor, will also increase slowly. Okay? Why? Because if you apply a voltage suddenly, like this. So, this is a battery, you connect this switch suddenly. Before that there was no charge across the capacitor. So, the voltage Vc was 0. Now, the moment you connect this switch, this potential is at a voltage Va. So, therefore, current will start to flow through this resistance, and therefore, this value of Vc will increase slowly with time, and finally, it will reach the value of this Va. Va is the battery voltage. Okay. So, this is also like a integrator circuit, precisely not integrator, it is not, this had it been a strict integrator, then for this constant input voltage the output should grow linearly and indefinitely like this, but this will grow exponentially and will saturate. But still this has the property that if you give an input here at this point and if you consider this as the output, the capacitor voltage, it increases. If you apply a positive voltage, this voltage increases. If you apply a negative voltage, this voltage decreases. Okay? This is kind of integrator, not precisely integrator. Now, what we will do? We will take this circuit in place of this integrator and we will use a Smith trigger. Okay. So, now this Smith trigger will have an input and an output. What we shall do, just like what we did in this circuit, we will connect the output of this Smith trigger to the input of this circuit. Okay. And therefore, if this voltage is at any moment positive, then this voltage will increase slowly, and what we will do, we will connect this to the input of this Smith trigger, so that if this is positive, this will increase continuously, and at some point this will reach some threshold, maybe the upper trigger point, and it will force this Smith trigger to change its output from positive to negative. Okay? And then it will be negative, and if this is negative, then the negative voltage comes here. So, this voltage will gradually drop, come down, and at some point it will be low enough to force this Smith trigger or trigger this Smith trigger to change the output once again from negative to positive. So, this way it will oscillate forever. Okay. And now, let me ask you a question. Which type of Schmitt trigger is it? Is it should it be a inverting type Schmitt trigger or non-inverting type Schmitt trigger? Okay. Which type of Schmitt trigger should we use here, means in this circuit? Can you answer? Just observe that what we want. We want, if this voltage is positive, then we know this is positive, then this voltage will go up with time, and then this increased voltage should cause the output of this Schmitt trigger to go down. Okay? And similarly, if this voltage is negative, then this is negative. So, this voltage is now coming down, and this going down voltage should cause the output of this Schmitt trigger to go up. So, what we want is a inverting type Schmitt trigger, because when input increases, output should go down and vice versa. So, the answer is we need a inverting type Schmitt trigger. This is what we need. Okay. And let us draw the circuit of this inverting Schmitt trigger and make this circuit complete. So, to draw the inverting type Schmitt trigger, I always start from a non-inverting amplifier. Okay. So, this is a non-inverting amplifier, and now I will change the plus minus sign, positive feedback and input at the minus terminal. Let us verify that this is a non-inverting this is a inverting Schmitt trigger. Say if I if at any moment this voltage is positive, the output is positive plus V supply. Okay. So, let me, this is plus V supply and minus V supply. If this is plus V supply at any moment, and if I want to make it minus, what do I have to do? So, I have the input here. To make it minus, to make the input minus, I have to make this voltage higher than this voltage. So, I have to increase this voltage higher than this voltage. So, input is to be increased if I want the output to go to minus. Okay. So, this is a inverting type Schmitt trigger. Fine. And just before this, we will connect this RC circuit, which acts like a kind of integrator. C R, you connect this here. No, sorry, this comes from the output to the input, and this output goes there. Okay. So, this is a oscillator circuit. Okay. This is a astable oscillator circuit. Why oscillator? Because you know this output will change from negative and to positive and positive to negative forever. Now, can we draw the voltage waveforms at different points? Say here, call this V c, capacitor voltage, and call this V o, output voltage. Let us try. So, time versus I shall draw Vc and Vo. Say let this be the output, let this be the Vc time. To start our analysis, as always, I shall start with some assumption that initially the output voltage is positive. Say this is equal to V supply plus V supply. This is minus V supply. So initially the voltage is positive here, and we shall take some value of initial voltage Vc. Let this be it can be anything, 0, positive, negative. Let us say it is here. Okay. This is the guessed initial value. Then what will happen? This voltage comes here, and therefore the capacitor will charge exponentially like this, and it will try to go to what? To which value? This will try to go to this the height should be plus V supply. Okay. So, this will try to go to plus V supply, which is the voltage applied here. Okay. But will it reach there? Maybe not, and in fact not, because let me mark two important voltages here, which are the upper trigger point and the lower trigger point of this Smith trigger. Okay. And let me call this R2 and R1. So, we can calculate what is upper trigger point and what is lower trigger point. Okay. So, what will happen the moment it reaches this upper trigger point here, it will not increase any further. It will come here, and at that moment, okay, the output will change from positive to negative. So, here it goes to minus V supply, and now this minus V supply comes here. So, this is minus V supply, this is also minus, and therefore, this capacitor voltage will start to drop. And where will it try to go? It will try to go to minus V supply. Let this be minus V supply. Then it will try to go to that value exponentially like this, but it will not be able to reach that point, because before that, at this point, when this voltage reaches the lower trigger point of this mid trigger, the output of this mid trigger will change again from negative to positive. So, here the output will become positive. Okay. So, this way this process will continue. Now, it will again try to go to this value plus V supply, but the moment it reaches this upper trigger point here, the output will change again, and this will continue, right. Now, so we know how it will work. Okay. Now, let us ask some small questions. Okay. So, for example, what is the value of this UTP and LTP, or that means what is the range between which this capacitor voltage oscillates. Okay. So, let us find it out. Okay. So let's find out UTP. We did it before, so we will do very quickly. I will not write a lot of details. So to find UTP, we will assume that initially say this voltage is positive. So this is also so this voltage is positive. Then we will ask what value of Vc will make it negative. So this value is positive assumed, and we will ask what value of Vc will make the output negative, right. So what is that value? So this is positive. If this is positive, means plus V supply. So the value of the voltage that we have here is it's R1 V supply by R1 plus R2. This is the voltage which is here. Okay. Now to make the output negative, I have to make this input higher than this. So I have to make this input higher than this. So the threshold is this R1 by R1 plus R2 times V supply. This is UTP. Similarly, LTP, you can verify it yourself. This will be minus V supply R1 by R1 plus R2. So then hysteresis band is this minus this. So it will be 2 R1 by R1 plus R2 times V supply. So this is the range, this is the height between which capacitor voltage varies. Now let us ask, so what is the frequency? Or time period? Okay. So the time period is here to here. So this is time period. Okay. And also you see that these two halves are symmetric. Okay. So this and this are symmetric. So therefore these two times are same. So if I call this time as T1, then time period is 2T1. So let's find the value of T1. You can also find this value, and so if you add them, you get the total time period. Okay. So let's call this T2. Okay. So let's find any of them, T1 or T2. So say we find the value of T2. How do we do that? So here you see the capacitor is being charged from a value of LTP, okay, and it is reaching the value of UTP. So what will be the expression of capacitor voltage then? This we shall write as the target voltage minus target minus initial times e to the power minus t by time constant. This is the rule that we also used yesterday. Okay. Now, what is the target voltage? Where is this capacitor voltage trying to go? It is trying to reach this plus V supply here. It is trying to reach plus V supply. So, this is V supply minus V supply minus initial. Initial value is, let us call it LTP, and the value of LTP is given here. So, we can put the value also. This multiplied by e to the power minus t by tau. What is tau? Tau is nothing but r times c. This r and this c. Okay. So, if I call say this as time 0, this point let us call it time 0, and then this time is how much? T, this is equal to t equal to t2. Okay. So, if we put the origin here for ease of writing, for simplified writing, so then this total time is t2. Okay. So, then we can write that Vc at time t2, which will be same as, so at this point it will be how much? It will be upper trigger point, equal to upper trigger point. And the expression for Vc we can write, we know this is V supply minus e to the power minus t2 by tau. Okay. So, from this what do we get? So, upper trigger point is equal to V supply minus or let me write it this way. Let me bring this upper trigger point to the right side and this term on the left side. So, I have V supply minus lower trigger point, this multiplied by e to the power minus t2 by tau, this will be equal to V supply minus upper trigger point, V supply minus upper trigger point. Okay. From this e to the power minus t2 by tau, this will be V supply minus upper trigger point divided by V supply minus lower trigger point. So, take a log on both sides. So, what we will have or before that you can write this T2 plus by tau is V supply minus lower trigger point. From this we write T2 by tau is equal to ln this entire term V supply minus lower trigger point divided by V supply minus upper trigger point. Please take my calculation also. Yeah. And from this T2 will be, so tau multiplied by this and the value of tau is RC multiplied by ln okay. So, this is T2, time period will be 2 T2 and frequency is 1 over time period. So, you can put this value here, which I am not doing, and you can also put the value of LTP and UTP in this expression using this. Okay. So, you can now put the values and complete this, I believe. Okay. So, that is about this particular circuit. We shall now go to another circuit. Before that, let me just tell you that I already have said that this is called an astable oscillator circuit. What is meant by astable? Astable means unstable. Okay. This is something which cannot which is not happy in either high output or with low output. When the output is high, after a while it makes the output low, but even then it is not happy. After a while it makes the output high. Okay? This is like a circuit which cannot decide and get to a fixed value. Okay? So it keeps oscillating, it's unstable. It cannot make up its mind which value it should take, something like that. It's a madman. Okay? So we shall talk about two more things which you have possibly heard is, so astable we already have said. There is something called monostable oscillator, and there is also something called bistable oscillator. So here in this context, we mean that in this context that an oscillator has two states or maybe two outputs like high and low, okay, plus and minus, something like that. And an astable or unstable oscillator is like a madman who cannot decide which state he or she should be in. So he or she keeps oscillating between two states continuously. A monostable oscillator is one which likes one among the two states. Okay. So let me just give you some small example. Maybe say if I just have a pendulum, okay, and where there is no friction, no loss. So if you bring it to the right side, it will come back and go to the left side. But when it goes to the left side, it again comes back to the right side, and it keeps on oscillating forever. So this is unstable, astable. Now let's think of another pendulum where say we have a wall, a soft wall or a cushion, and the pendulum is hanging from here. Okay, so it has two states. The two states, we are defining two states as this is one state. So this is one position, and the other position is say here. If you bring this here, it will always come back and stay here. It will not bounce because of the softness. So it has two states, 1 and 2, but this likes this state 1. If you bring it to state 2, it will go back to state 1. So this is the preferred state. So this is called monostable oscillator. Okay, so this pendulum is happy in one among the two states, but is not happy in the other state. So if you bring it to the other state, it will always come back. After a while, it will take some time to come back. Okay, but here there are two states, the left and the right, and the pendulum is not happy in either of the two states. Okay, and there is something also called bistable, and this you can think that okay, there is a table on which there is a ball rolling, and you can keep the ball either on the left side or on the right side of the table. Okay, and it's a flat table. So if you bring it to the right side, it will stay there. If you bring it, if you keep it to the left side, it will stay there. It's like a so these are the two states, 1 and 2. And we are, note that we are not considering any other intermediate position as a valid state. We are not considering that at all. Okay. So, the only two extreme positions, left and right, we are considering here. Similarly, here the extreme left and extreme right we are considering here also. Intermediate states we are not considering. So, here this is bistable. Okay. Now, the circuit that we have seen here, this was unstable or astable because it has two outputs, two states, low and high. When the output is low, after a while it goes to high, and if it is high, after a while it goes to low. So, it was unstable. Now, let us make a monostable oscillator circuit. Okay. We shall start from this circuit and will modify it. What we shall do is that we shall put a extra diode okay. So, this is a new thing we are adding. So, how does it modify the behavior of this circuit? Observe that value V c cannot go above the forward voltage drop of this diode. Okay. So, cannot go above, call it V f d, which is the forward voltage drop of the diode. Okay. So, why this voltage will not go beyond that? Because this voltage is high, always can be high. This can be plus V supply, which is plus 15 volt, but this voltage forward drop is something around 0.7 volt for a silicon diode. Okay. But this is say 15 volt. So, we have 15 volt applied here, and say initially the capacitor is not charged. So, this voltage is 0. So, this 15 volt will charge this capacitor, current will flow through this R and this capacitor will get charged. So, this voltage will then increase, and the moment it increases to the level same as 0.7 volt, then this diode will be on and this will act like a short circuit. So, the entire current will flow through the diode and will not go to the capacitor. So, the capacitor voltage will not increase any further. Okay. The entire current will bypass through the diode. Okay. So, the capacitor voltage cannot increase. Okay. So, therefore, let us see what is the implication of this fact. Okay. Say if V c, which is this voltage, okay, that is capacitor voltage, is negative at some moment at a point of time, then what will happen? This is negative, and let us say this is plus V sub, this is output is positive, and V o is positive. then Vc will increase because current is flowing through the R, resistance R, up to VFD and stop. So, Vc will not reach upper trigger point of this mid trigger. So, VO will not be negative on its own. Okay? So, if the output is positive, it is not going to switch back to negative. So, VO will not be negative. Now, let us see what happens if the output is negative initially. Okay? Now, say VO is negative. Okay. So, somehow the output is negative initially. Previously, we have seen here the output was positive. So, this is case 1. So, let me write this is case 1. Case 1 where the output is positive and therefore, Vc will increase, but it will not reach upper trigger point. So, output will remain positive forever. And this is case 2 where we start with the assumption that the output VO is negative somehow, anyhow, okay, somehow it is negative. Then what will happen? Then this is negative. So, then the capacitor will charge to negative voltage, then Vc will go down towards minus V supply. But before that, but at a point this voltage Vc will reach or will come below the lower trigger point of the Smith trigger. Okay? So, it will come below the lower trigger point and then what will happen? The output will change. Then VO will change to, initially it was negative, so now it will become positive, change to plus V supply. Okay? So, then the output goes to plus V supply, and once this is at plus V supply, so then capacitor voltage Vc, this will start to increase. Vc will start to increase and reach this voltage, the forward drop of this diode, maybe 0.7 volt, will reach VDF and stop. Okay. So, Vc will not reach upper trigger point. Okay. So, it will stop there with the output being positive. So, what have we seen? Let me summarize. Case 2, if the output is negative, then this will make this voltage more and more negative, and then the lower trigger point will be reached. So, the output will become positive. We started from negative output, but we went to positive output. But case 2, once this is positive, this will try to increase the capacitor voltage, but will not be able to increase it beyond 0.7 volt. So, we will not reach the upper trigger point here. So, output will remain positive. So, positive output is a stable output. Once we are in positive output, we will remain there forever. But if we by chance go to negative output ever, that is not stable, the output will become positive very soon. Okay? now you should ask that how can the output be negative ever? Okay, because we saw the positive is a positive output is a stable output. So how can we make the output negative ever? So the question is, how can we make the output negative ever? Okay, and the answer, the only I mean not only, the one answer is that if you by force make this higher than this, by force, by some chance, or which means you have to make this voltage, okay, this is called this Vp Vn. So if you by force, by somehow if you make Vp lower than Vn, okay, then the output will be negative. So for example, what we can do, say, I mean one possible way is take a battery and connect it. If you connect it, okay, if you connect this, then this voltage, this negative voltage is directly coming here, right? So the output will be directly negative, and if the output is directly negative, then this is lower than Vn, so output will be negative. So the answer is, so we have to make Vp negative forcefully. Okay, this is called triggering. Okay, and we shall continue about this in our next class. Okay, just think about it, that to make the output negative, we can forcefully apply a voltage like this. Somehow we have to make this negative. Thank you.